First, allowing me to revisit the stereochemistry of this complex, which we did remind last time is not optically active. Notice that when we had the complex, which is composed of the same set of ligands, ABC ligands, this complex, versus this complex, which is A3B2C. This, for the least symmetric geometric isomer, was found to be optically active. The mirror image of the least symmetric isomer of this, the all-cis isomer, is different from the all-cis version of this, whose image was cast into the mirror. Not so for this. The mirror image of this is identical. But I think the talk that I offered on that last time was pretty clumsy at best. So, what you realize from this is that even though these two complexes are composed of the same sets of ligands, same set of ligands, which of these complexes is in fact more symmetrical? Here is all cis A3B2C, and we've already recognized that all cis A2B2C2 is optically active. So which one is more symmetric? You remember we recognized that if any geometric isomer of a species is optically active, it will be the one which is least symmetric. This complex has an all-cis geometric isomer, which is optically active. This complex, with its all-cis geometric isomer on the board, same set of ligands, but different numbers, is not optically active. Which one is more symmetric? Has to be this one. Because the lowest symmetry isomer of this is optically active. We're looking at the lowest symmetry isomer of this, and it's not optically active. So, to pick up from last time, I've drawn the mirror image of this. And I said, or at least meant to say, pay attention to, in order to find out in shortest order fashion that this is not optically active, the AC axis. AC axis, because on the AC axis lies C, the ligand of which there's only one in the first coordination sphere. So, when I draw the mirror image, I'm going to hold this thing by the top and bottom atoms, A up top and B at the bottom, and I'm going to rotate it 90 degrees this way. I did that so I can make the AC axis for this version of this complex to be identical with the AC axis for this version of the complex. All right? Now, after having done that, at first glance it might seem that this is different from this. We know this is this. Again, I just took a hold of this and I rotated it 90 degrees so that A1 came over here and this A came over here and C came over here, B came over there. But now I've got the AC axis in identical orientation with the AC axis for the geometric isomer of this complex that we are attempting to demonstrate is not optically active, which means this and this are the same thing. Now, I'm going to hold this thing by A and C. So, if I've got the model like this, as you look at it, here's A and C. C, forward, toward you, left front corner of the canted square. All right? And now I'm going to rotate this thing 90 degrees along this AC axis. Like this. And again, if you don't have models, you can do this with a piece of paper and a pencil. But I will say to you, if you're going to go on and do more chemistry, the most, I think, the biggest favor you can do for yourself is buy a set of models, especially in organic class. There's no way to get through organic chemistry without a set of models. The stereochemistry is extremely important for organic molecules. Now, when we do this rotation, notice what happens. This B comes down here. I'm taking this, we're going to do this with it, 90 degrees. B comes here, this B goes to this corner, this A goes up top, and B to A, this A goes up top, and this A comes to this corner, and AC stay in the same position because these are the atoms which lie on the axis of rotation. And now we can see. Here's our AC axis. And by this rotation, this A went up top, this A went over here, so we've got the same AAA pictorial orientation as we have here, and B here, and C there. Now, what's different? If you number the other A atoms and number the B atoms, 1 and 2, or label them in some fashion, however you want to label them, you'll find out that for this complex, which is obviously identical to this complex because B's are the same ligands and A's are all the same ligands. But this A ligand is not the same as the A ligand over here. If this is A ligand number 2, then in the right side picture, A ligand number 2 is over here, and this is A ligand number 3. If in this picture, this is B1 and this is B2, then over here, this is B2, this is B1. But since B's are identical to each other and A's are identical to each other, these are the same things. But if these were different groups, then we would have an optically active species. Now, the next question is, from the notes, 2419. Here we have a complex composed of 3 different ligands. One is chelating ethylene diamine, bidentate ligand. How many geometric isomers? And does the least symmetric version, the least symmetric geometric isomer of this, does that show optical activity? In this case, the answer is yes. We take a look. AA trans, BB trans, and the least symmetric are the A's cis, while the B's are cis. If you now draw the mirror image of this, which is this, and as we've done before, take this, hold it by A up top and B down below, and rotate it 180 degrees, to put the ring over here, put the ring over there. We get this. And see what has happened to the positions of A and B in the canted square. Here, we had A behind the drawing surface and B out in front. Now we have A in front of the drawing surface and B behind the drawing surface. So that is truly optically active. The mirror image is different. Now, one more type of complex I want to take a look at. if for no other reason, you're going to look at molecules in organic class which show this behavior, the last isomeric behavior, stereoisomeric behavior, which we're going to take a look at. Take a look at this complex. 2A ligands, 2B ligands, and a C and a D ligand. So now we have 4 different ligands in the first coordination sphere, 2 of which are alike, and another 2 which are alike. We can ask the question, given that we've recognized that the least symmetric geometric isomer of this complex is optically active, that establishes that the least symmetric geometric isomer of this has also got to be optically active. Why so? Well, with C and D being different ligands from each other and different ligands from all the other ligands in the first coordination sphere, how does the overall symmetry of this for the least symmetric isomer compare to the overall symmetry of this for the least symmetric isomer? Which one is of lower symmetry? This one. So if that thing is optically active for the least symmetric isomer, this has got to be optically active. Because the least symmetric isomer of this has lower symmetry, is less symmetric than the least symmetric isomer of this. Now let's draw some pictures. I've labeled these 2 sketches with cap Roman 1 and cap Roman 2. A's are cis, B's are cis. A's cis, same positions as these A's. B's cis, same position as these B's. And C and D in the canted square, C and D in the canted square, but at what appear to be different corners. This D's out in front of the drawing surface. C is behind the drawing surface, whereas here C's out in front of the drawing surface, and D's behind the drawing surface. What we want to know is how these 2 geometric isomers for this thing compare to each other stereochemically. Does this look like such a complex? Well, let's take a look at a model. Let's see. I know what I want. Oh, these things are difficult. Back to this one. I can take this one apart a lot easier. Let's see. We want B out in front and down below. That's not getting us any place, is it? All right. A, B, B, this labels. And so, based on the labeling system I have on the board, the white one is C and the black one is D. Now let's take a look at this. We've decided that the green ones are A's and the red ones are B's. So we've got to make a couple of changes here. Red ones are B's, so this is okay. Now, red ones, green ones, which are A's, and I guess we decided the white one is C. I'll have to switch these. Wonderful. All right. Here's the one at the bottom. Here, 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 here. And the black one behind, the white one in front. As opposed to this, which is the model up top, where the white one is C and behind. Black one is here out in front. Red, red, which is this and this. Green and green, which is this and this. All right, we got the models. Now, how do these two geometric isomers compare stereochemically? That's the $64 question. Are they mirror images of each other? Well, I've drawn the mirror image of this, and I've drawn the mirror image of this. Let's hold them up like this. And we can see they're not mirror images of each other. If they were, then this would be a green to go with this green. And for this ligand and this ligand, this would be a green to go with this green. But not so. So we're looking at two geometric isomers for the same complex, compositionally speaking, same structure, both octahedral, both optically active, but not mirror images of each other. What are these things? So we add one more word to our language. They're diastereomers. Let's write that on the board. Diastereomers are optically active geometric isomers for the same species, so they're isomers of each other. But they're not mirror images of each other. Interesting. And makes the water even more muddy. But there's all kinds of organic molecules which show this muddy water behavior. And we're seeing now that we can find complexes which show this muddy water behavior. So with that, let's take a look at one last complex. And for this last complex, I'm going to consider this as a substituted version of ethylene diamine. Notice the similarity of this ligand to ethylene diamine. We still have two nitrogen donor atoms. This is an NH2 group, just like ethylene diamine, which has terminal NH2 groups. CH2, CH2 skeletal groups, just like ethylene diamine. Another nitrogen donor atom. But unlike ethylene diamine, this is not an NH2 group. For this group, I've gone to the laboratory and done some chemical synthesis to replace one of the hydrogen atoms with a methyl group. Now what have I done from a stereochemical standpoint? I've made the problem even more complicated. Why is that the case? Because this nitrogen atom by itself is optically active. Which means if I make a complex using this as a ligand, the complex is guaranteed to be optically active. Because I've synthesized the complex with an optically active ligand. Let's take a look. Here, I've drawn a nitrogen atom from an ammonia molecule. Kept one nitrogen-hydrogen bond intact. Replaced one of the hydrogen atoms with a methyl group. And imagine here to have replaced the other hydrogen atom with Cl, chlorine atom. Now I drew this rather than that because if I draw that over here, then the Cl would not, then instead of Cl, we'd have this CH2, CH2, NH2 group. Simulates. CH2, CH2, NH2 for ethylene diamine. Is this optically active? Yes, it is. Let's take a look. Model. The central black atom part of the model is nitrogen. I've attached 3 different peripheral atoms or groups to nitrogen. And there's the donor electron pair. Just like this. 3 different groups attached to nitrogen, but the same different groups as are attached to this nitrogen. A white one, a red one, and a blue one, and another purple non-bonding pair. I guess all non-bonding pairs must be purple for this consideration. How do these compare? Well, if I hold the models like this, I can see at a glance these are mirror images of each other. Here's the mirror. There's the whites looking at each other, the reds looking at each other, the blues down below. And the way I've held the models is the purple non-bonding pairs are each pointing in opposite directions relative to each other. How can I prove these are different? We try the superimposition test. And if I lay the non-bonding pairs to be coincident with each other and the blues to be coincident with each other, we see that the reds and whites are not coincident with each other. Just like right hand, left hand. Also optically active. So you can see that coordination chemists, from a stereochemical standpoint, will have one hell of a lot of fun if they use optically active ligands to make complexes. And they do this stuff. I've drawn an example of such. Model. Now I'm sorry that the model is small, but I think it's large enough for you to see. I bought these models a year ago, hoping that they would serve the purpose of replacing the models which have become broken or missing from the collection of model parts we have in the back. And found out that with these things, I can make all kinds of models. More so than what I can make with the parts in the back, because these spherical central atom representers have all kinds of holes in there. So I can make sp3 atoms and sp2 atoms and sp atoms and sp3d atoms and sp3d2 atoms and sp3d3 atoms and sp3d4 atoms. I can make all kinds of stuff. sp3d4 is an interesting hybridization. sp3d4. If we have peripheral atoms rather than peripheral groups, and I have an sp3d4 hybridized central atom, how many peripheral atoms bound to the central atom? If all the sigma valence electron pairs for the sp3d4 hybridized central atom, if all its peripherals, if all its sigma pairs are connected to peripheral atoms, they're all bonding pairs. How many atoms will be connected? 8. What do you think the geometry is of a complex which has got an sp3d4 hybridized central atom, 8 bonding pairs, and all the peripheral atoms or groups are identical? What do you think it'll look like? I'll draw a picture on the board as a possibility. You ever seen an object like this? And just for fun, when you were a real little kid, did you play with baby blocks? You did? I did. I mean, when I was a kid, computers, hell, we didn't even have TVs yet. We had radios. Okay. So I'd sit in the front room floor on a rug and listen to the radio. Radio was a huge thing. Big wood cabinet, little radio guts inside there, and a record player inside, which in those days was called a Victrola. It was made by RCA Victor, same RCA company as today. I can tell you that when they started to make nice vinyl long play records and the like, you didn't want to play those on the old Victrola because it had a tone arm that weighed about 2 pounds. So the stylus was more like a large nail and would scratch and ruin records. But never mind that. What counts is the baby block activity. You know a cube has got 8 corners. And a cube is a very symmetric object. The central atom is here. And you got 1, 2, 3, 4, 5, 6, 7, 8 ligands. If we have, for this cube, an sp3d4 hybridized central atom, and all the atoms at the corners of the cube are identical, question: for this type of coordination and hybridization, sp3d4 central atom, 8 sigma bonding pairs, no non-bonding pairs, and all the atoms connected by the bonding pairs are identical. Okay? Would this complex, would this chemical species be a cube? What would it be? Well, maybe you don't know the name for it. But what would I do to my cube to turn the shape of the complex that I'm describing? Pardon me. Regarding the shape of the complex that I'm describing, what would I do to my cube to turn it into this shape? Did you learn in 2045, when you started to talk about sp3 hybridization, with 4 bonding pairs and no non-bonding pairs for the central atom, and found out that the resulting species was not a square? Because if I have a central atom here and a square pattern of like atoms around it, that's very symmetrical. But is there a more symmetrical arrangement of these 1, 2, 3, 4 bonding pairs? Is there a more symmetrical arrangement? Yeah, it's tetrahedral. Because we got to remember, these atoms are three-dimensional objects. Valence shells are spheres, not circles. So, if I'm in my mind's eye, I'm looking at this square. I got my central atom here, and an atom here, and an atom here, and an atom here, and an atom here, in this square pattern. What do I do to the square to turn it into a tetrahedron? Well, how do I twist? Atom, group, atom, 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 atom. Central atom, atom, atom. Let's keep these 2 bottom atoms right where they are, okay? Atom, central atom. Atom here at the corners of my square. Now let's take the 2 top atoms at the other corners of the square. The 2 top corners, and I'm going to take these 2 top atoms and do this. Now if I connect these, central atom, central atom, central atom, central atom, this orientation for the top atoms, and this orientation for the bottom atoms. If I now connect with lines the positions of the peripheral atoms to the central atom, I got a tetrahedron. You think I can do the same thing with this? And achieve a geometry which is even more symmetrical than the cube? Let's leave the 1, 2, 3, 4 bottom atoms in place geometrically. And take these 1, 2, 3, 4 top atoms. Let's take the top square and rotate it how many degrees? Then I'll have the same thing. 45 degrees, that's right. So I'm going to take the top and make it like this. Up. This is going to come over here, this over here, this over here, and this over here. So let's see if let's just do it like this. Now, I'm going to quit this because trying to draw this three-dimensional object on a flat surface, which is two-dimensional, and show you in fact what it looks like is difficult. But what I am trying to draw you is called a square antiprism. I don't care that you know its name. If I wanted you to know its name, I'd write it down. But it's interesting. Take your cube. Take the top square or the bottom square or any of the face squares, doesn't make any difference, and twist it 45 degrees while maintaining connection of the atoms at the corners of the cube to the central atom. And you'll get a square antiprism, which is a more symmetric geometry than the cube itself, because it winds up putting the non-bonding pairs, the bonding electron pairs, further from each other than they are in the perfect cube. Just like when we had the square, okay? When we have the square, what angle do we have between the peripheral atoms? What angle do we have the peripheral atoms and the central atom together? You know what we have. Take a square. "90 degrees. Now remember what we achieved? by keeping the two bottom atoms in place, or the two top atoms, doesn't make any difference, and taking the top atom doing this. What happened to the bond angles? What are the bond angles for a perfect tetrahedron?
120.
Bond angles for a perfect tetrahedron? 109. 109.45 if you want to take it to two significant figures. So recognize, we've kept the peripheral atoms the same distance from the central atom. We haven't changed bond lengths, but we've changed positions occupied by the peripheral atoms. They now form an object that looks like a tetrahedron. It is a tetrahedron. And the bond angles increase from 90 degrees to 109.5 degrees. Well, didn't that make the bonding electron pairs get farther apart? And the farther apart you get these electron pairs, the less Coulombic repulsion you have among them between the electron pairs. We achieve the same thing when we take the cube and turn it into a square antiprism. Now, I'm not of a mind to hold you responsible for this issue, but it's the kind of stuff that you have to think about if you're going to do stereochemistry. You got a question?
I was wondering if the dimensions of the flat faces of the square antiprism are dimensionally the same as the square. Are they the...
Yeah, we haven't changed any bond lengths.
Elongated or should...
No. No. For a square antiprism, each face is still a perfect square. The top face, bottom face.
Like same perfect square as before it was twisted? The same dimensions?
Yeah.
Okay.
Haven't changed any lengths. Okay. So let's go back to this last complex that we want to look at. Of this general composition. Now we've got 4 like ligands, all ammonia molecules, or whatever you want them to be, as long as they're identical. And 1 chelating ligand. Except that our chelating ligand now is not purely ethylene diamine, it's this substituted ethylene diamine, which contains an optically active nitrogen atom. And this I forgot to pay attention to the complexities when I first wrote question 4 on the bonus quiz. That's why I went back and changed it. Because you introduce all kinds of new stereochemical properties for the species when you start using ligands which themselves are optically active. How about this model? Does it look like a model of what we have on the board? 1, 2, 3, 4 identical ligands, the little white spheres. I could have used different colors. I mean, I could have used larger modular representations. Okay. You can imagine these are hydrogen atoms. Who cares? The big white sphere and the big blue sphere are nitrogen donor atoms. Here's a coordinate covalent bond, here's another coordinate covalent bond, and here's my chelate ring. This is the NH2 donor atom. CH2 over here and CH2 over here. But here's the optically active nitrogen. So imagine this is a hydrogen atom and this is the methyl group, because clearly a methyl group is a lot bigger than a hydrogen atom. All right? This look like the same thing? 4 identical monodentate ligands in the first coordination sphere. My chelating ligand is this substituted ethylene diamine, just like it is over here. Red again represents the methyl group on this donor nitrogen atom, and white represents the other atom on this donor nitrogen atom. Here's a mirror. These look like mirror images of each other? There's the little white ones looking at each other, the top white ones and the bottom white ones looking at each other. the white nitrogen atom over here, white nitrogen atom over here looking at each other, and the up top red methyl group, they're looking at each other, and this simulating a hydrogen atom is closer to me than it is to you, closer to me than it is to you, looking at each other. Mirror images of each other. Because of this, and optically, and different because of the optical activity of this substituted nitrogen atom, simulated by blue in this model. Now, what's going to happen if I take this chelate ring and break this bond and break this bond and I rechelate? Oh, fall apart. I was meaning to tell you about these models before. I can do all kinds of things with these models, but I found out that the parts are very fragile. And I have on occasion spent a good deal of time making models like this to show folks like yourself and have the damn thing break just when I want to show it. That causes me to say a lot of four-letter words like heck and darn, things like that, you know. What do we got now? Well, compositionally we still have the same thing. Shape-wise we still have the same thing. Let's see what we have. Are these mirror images? By golly, they are. Aren't they? Still mirror images of each other. Not identical. Well, let's try another bond break, bond make. All right. I'm going to take this methyl group. Whoop. Come on off of there. Put it over here. All right. What do we got now? Well, they're not mirror images. What are they now? What do they look like? Are they the same? Notice the blue, which simulates the optically active nitrogen, has the white one oriented that way and the red one oriented that way, just like this one. Okay? And you can see the orientation of the other four, same as these. Well, can I overlay these things? No. Notice what's different. Now, this nitrogen atom is on this side for the top complex, and the nitrogen atom's on this side for the bottom complex. Well, then let's turn this thing over. Okay? Now the nitrogen atoms are in the same place, and the donor blues are in the same place, but now these are projecting up, whereas these are projecting down. Well, I can fix that. By this. Because remember, these are single bonds, so I can rotate freely along these bonds. Are we the same? All the little white ones are overlaid, and the chelate rings are overlaid, and the white NH2 donor atoms are overlaid. But what about these? What about the optically active nitrogen? Are they superimposed? Do you see a difference in bond angles? What I now have is a diastereomeric pair of isomers. Now, with more bond breaking and remaking, I can, of course, turn these into each other. So you see the complexity from a stereochemical standpoint that we introduce to a problem like this. When you use a ligand that itself is optically active. Clearly, these can, if I make two different models, they can be the same thing. Or we can make the mirror image of this one, which is what I have here. But if you do this, which is what we just did with the model, you see how these CH3 and H groups here, I'm imagining that the CH3 is projecting up and the H is projecting down. Here the CH3 is projecting and the H is projecting up. That's what we just did with the model. These are diastereomers. Complex. At least, pardon me, I should say complicated. But you're going to see all kinds of this if you do more coordination chemistry studies, and assuredly if you do organic chemistry. Now, enough on the stereochemistry. For the rest of today's conversation and tomorrow's conversation, we're going to pick up with and conclude what I had hoped you would have discussed in entirety last Thursday, but after I put together the lesson plan, I knew it was too much. But as usual, all the discussion gatherings didn't make the same degree of progress. I do think that most of you, but not all of you, were able to discuss the chelate effect. How many did not talk about the chelate effect last time? Well, everybody talked about the chelate effect last time. But in brief, if I make a water solution of a complex like this, nickel hexamine in the most common oxidation state shown by nickel in its chemistry, which is +2. And treat this in water solution with ethylene diamine. In excess. Then I will observe that on standing, because we're not paying attention to the kinetics of this problem, that all the ammonia molecules, even though they're strong ligands, they coordinate effectively. All the ammonia molecules will get kicked out of the first coordination sphere and replaced by ethylene diamine. So we now have turned a complex with 6 monodentate ligands in the first coordination sphere to a complex which has just got chelate rings and 3 chelating ligands, and at the same time liberating ammonia molecules to the solution. And since you all talked about this, at least that's what you just told me in discussion class last time, you recognize that this thing is driven very strongly by a large change in delta S. Because if you put this reaction on a mole basis, then we've got 4 moles of reactant particles, 1 mole of complex, 3 moles of ethylene diamine, being converted to 7 moles of product. 1 mole of complex, and now 6 moles of the previously monodentate ligand ammonia molecules. So on a mole basis, what does this change look like from an Avogadro's perspective? Well, in Avogadro's number, the 3 sig figs is 6.02 times 10 to the 23rd. So we took 4 times 6.02 times 10 to the 23rd particles in the system and turned it into 7 times 6.02 times 10 to the 23rd particles in the system. Does entropy like this change? You betcha. Entropy says, wonderful. And that's the thermodynamic driving force which underlies this so-called chelate effect, because in essence, the chelate effect is a case where you're taking monodentate ligands and replacing them in the first coordination sphere by polydentate ligands. Now, what if I did this? What if I started with nickel, with hexaaqua nickel plus 2 octahedral complex with monodentate water molecules rather than monodentate ammonia molecules? Well, at a glance you see that this too is also strongly driven by a big change in entropy. 4 moles becomes 7 moles. Now, from a thermodynamic standpoint, what's the other part of the puzzle? Well, the overall thermodynamic standpoint is reflected by delta G for the reaction. Change in free energy. But what are the puzzle parts of which delta G is composed? Delta H and delta S, with delta S being multiplied by T. Now we also know that if we study this reaction under standard state conditions, and can get the change in standard free energy for this reaction at our temperature of choice, which is probably 298 K, then we can get the equilibrium constant for the reaction. And we've done a whole bunch of equilibrium analysis for various and sundry reactions this term. I trust you certainly recognized that when you looked at part 1 of the last exam. Well, what if we want to look at these two reactions from an equilibrium analysis standpoint? In this case, or for this case, here's ammonia. How does the donor strength of ammonia compare in general to the donor strength of ethylene diamine? In general, how does the donor strength of ammonia compared to the donor strength of ethylene diamine? If on the last exam I asked you to talk about the Lewis-based coordination ability of ammonia versus the Lewis-based coordination ability of ethylene diamine, what would you say? If all you tell me is ethylene diamine is stronger, all you've given me is a vote. The question is worth 20 points, you got 1. Because I have not heard any explanation. I'm saying, in general, how does the donor strength of an ethylene diamine nitrogen atom compare to that of the nitrogen atom for ammonia? There's an ethylene diamine nitrogen on the right. a perfect ethylene diamine nitrogen. You see that these nitrogen atoms are very similar? They're both sp3 hybridized. They both have hydrogen peripheral atoms. For ammonia, you got 3, and for ethylene diamine nitrogen, you got 2, plus this carbon skeleton part. How's the electronegativity of carbon and hydrogen compare? Which one is more electronegative? Hydrogen or carbon?
Hydrogen.
Fluorine 4.0, oxygen 3.5, nitrogen 3.0, carbon 2.5. Now, since hydrogen is the most common elemental component of material, it's to our benefit to keep in our memory banks the electronegativity of hydrogen. What is it? 2.1. 2.1. So carbon is somewhat more electronegative than hydrogen. But based on the extreme similarities of these nitrogens as donor atoms, they're both sp3. They both have peripheral hydrogen atoms. The only difference is an NH single bond versus an NC single bond, with the electronegativities of carbon and hydrogen being not too far apart. So I repeat my question in general. How do the donor strengths of ethylene diamine and ammonia compare? Very similar. How do the Bronsted base strengths compare?
Very
Similar. Look at the acid-base table. You still got it? What you're looking up now is you're going to look for Kb ammonia versus Kb ethylene diamine. And you can find that by looking at Ka for ammonium ion and Ka for the ethylene diamine molecule when it's been singly protonated. This is on the acid-base table. I put it there purposely for this particular conversation. Which one is the somewhat stronger acid? Ammonium ion or protonated ethylene diamine? Ammonium ion. Well, if that's a somewhat stronger acid, then ammonia is a somewhat weaker base, but very similar. So keep in mind regarding these two reactions. This reaction is driven extremely by delta S and only slightly by delta H. This ethylene diamine is only a very slightly better donor than ammonia. But this reaction is not only driven by a significantly favorable change in entropy, this reaction is also driven by a significant improvement in bond strengths. Delta H is very exo for this reaction, because now water molecules are being kicked out of the first coordination sphere rather than ammonia molecules. And we know that water molecules are not nearly as good as Lewis bases as are ammonia molecules or ethylene diamine molecules. So that leaves me with one remaining consideration regarding this particular issue. I mean, first, before we consider this issue, notice that the chelate effect is an entropy-driven effect because you're turning a first coordination sphere showing monodentate coordination to polydentate coordination. But it can also be strongly supported by delta H, like this thing turning into a chelate complex versus this thing. So the last part of this puzzle is nitrogen donor from ethylene diamine, nitrogen donor ammonia. We have recognized that the ethylene diamine nitrogen is a somewhat stronger Lewis base than is the ammonia nitrogen. Why is this? Because the only difference, single NH bond versus single NC bond. And the electronegativity of C is greater than the electronegativity of H. This is 2.1 on the Pauling scale. This is 2.5 on the Pauling scale. Do you recognize that if we assess induction based on atomic electronegativity, we would argue this thing with a higher electronegativity is electron withdrawing relative to this. What's that term mean, electron withdrawing? You remember what chlorine atoms do if they're part of the skeleton of a molecule, or fluorine atoms if they're part of the skeleton of a molecule, or oxygen atoms if they're part of a skeleton of a molecule regarding the development of negative charge? They stabilize negative charge development because they're electron withdrawing due to their high electronegativities. Well, we looked at another electronegativity comparison here. Atomic electronegativity. Carbon is more electronegative than hydrogen. Well, that ought to make this nitrogen's non-bonding pair more stable than this nitrogen's non-bonding pair. Because the only difference is an NC single bond versus an NH single bond. So based on atomic electronegativity, I expect this carbon atom, because it's more electronegative than this hydrogen atom, I expect this carbon atom to stabilize non-bonding electron density on nitrogen inductively more effectively than the hydrogen does to the non-bonding pair on the nitrogen atom in ammonia. From an atomic electronegativity standpoint, that's the conclusion I reach. But the facts is this is a better donor. So let's proceed one step beyond atomic electronegativity and bring back into the picture this. What's this? Orbital electronegativity. Is a hydrogen atom hybridized? No. Hydrogen atom can only use its 1s atomic orbital period for any bond interactions that it is associated with. How about this carbon atom? We talked about it from an atomic electronegativity standpoint. How's this carbon hybridized? What is it? Tell me and I write it down. sp3. And these orbitals are from what energy level? 2. So, I ask this question, from an orbital electronegativity standpoint, do you expect the 1s atomic orbital of hydrogen to stabilize more effectively or less effectively valence electron density than an sp3 carbon? Which atom? From an orbital electronegativity standpoint. 1s hydrogen versus sp3 carbon. Which atom stabilizes valence electron density more effectively? The 1s hydrogen or the sp3 carbon? The 1s hydrogen. Does that support the facts here? You betcha. So that's the argument we'll use. We'll pick it up from this point.